Okay, that helps us in this case. It happened to be an endpoint, right, in our original problem. Okay, fine. That tells me whether or not that endpoint converges or diverges. But that's not. I mean, but that's not what we're looking here. We're just literally, what does this series do? Does this series converge or diverge, right? And so the series 1 over n to the 1/2 only converges if it's -1 to the n over n to the 1/2. Otherwise, it diverges. Okay, so that's a conditionally convergent series proven by the alternating, series test. Okay. So again, you got to test for absolute convergence first, and if that is a no, then see if it alternates and see if it hits these 3 statements here. If it does, then the series converges conditionally. Right? So if we come back and try to answer, these questions here, okay, I'm not sure how important they are in the realm. The interval of convergence is the most important idea, although it is important to know whether it's conditionally or absolutely convergent. Okay, so the interval of convergence. Let's talk about the first question, which was this one. All right. So what did we find out in the first problem? What our interval of convergence was? -3 to 3. Inclusive, right? Right? Which is also where it converges absolutely, right? So absolutely it would be -3 to 3 inclusive. And where did it converge only conditionally? Where? Nowhere, right? So there's no spots where it converges conditionally, right? So none. Okay. In the second example, when it was n to the 1/2, what was my interval of convergence? -3 to 3. Non-inclusive, whoops. Sorry, -3 to 3. Included at -3, right? It worked there, right? It converged there, right? The series converged at -3, right? Okay, by the alternating series test. Okay. Where did it converge absolutely? This was based on the ratio test, right? The ratio test that it worked from -3 to 3, right? And where did it converge conditionally? At x equals -3. Okay? So conditionally convergent is only ever going to be at a point. Right? So conditional convergence is never on an interval. Right? Because again, when we did the ratio test, we were testing for absolute convergence. Right? That's what produced the interval. Right? So this was our first part. Right? Then when we tested the endpoints, -3 worked, but it only worked conditionally. Right? +3 diverged no matter what we did with it. Okay? And so the absolute convergence was -3 to 3. The conditional convergence was just at -3. Okay. So again, as you go through and look at these, right, again, you're testing absolute convergence first. Again, when it wants an interval of convergence, like ratio test, right, that's our big test for that, right, so do your ratio test on it. Again, that's going to give you an interval, typically, right, where it's absolutely convergent. Okay. Then test your endpoints. Okay, and again, when you test your endpoints, you get a whole new series. Right? You get a series without any x's in it. Okay, and you got to go through all those tests from the other day, right? We wrote down 7 or 8 different tests, right? Direct comparison, limit comparison, nth term test, is it geometric, p-series, integral test, right? Ratio test, right? Those all test for absolute convergence. Those are all testing for, with the exception of the nth term test, that's testing for divergence, right? Not convergence. Okay? Those are all tests. They all get to have positive terms in them, or otherwise we're not talking about it. Okay. If that doesn't work, then ask yourself, hey, is this an alternating series, right? Right? And again, you want to think about writing out those terms. Again, that's why it's really critical to have it written this way, right? If it's written this way, I know it's alternating, right? You can just see it right from there. Go through with it. All right. All right, so why don't you try, let's do this problem here. So nx to the n over 4 to the n times n squared plus 1.